Hey, how's it going? My name is Brody Marino. Here's my final project for Mateo Boy's digital signal processing class. We were tasked with creating a automatic beat detection algorithm for an ICP signal. So we did this in MATLAB. And so basically what I'm going to do is I'm going to walk through the code step by step and kind of show you how we arrived at the final output. I can show you bits and pieces. I'm not going to go too in depth in the code, but I'll show you what each portion of the code adds to the project, and in turn provides a working beat detection algorithm in the end. So we were given an online file that had an ICP signal already created for us. So if we go ahead and run this section, it's basically just going to plot that signal for you. This is going to be the ICP signal. And as we go further down, actually let me zoom in here real quick. So basically what we're supposed to do is if you zoom into the signal, you can see peaks up and down throughout the signal. So peak here, peak here, peak here. And basically throughout the whole signal there's these peaks, and we're tasked with creating an algorithm in order to plot the peaks of this signal. So there's our given signal. So the first step, actually let me bring it back up for you. If you notice, there's actually a DC offset. So the first step is to obviously eliminate that. In order to eliminate that, we are using a high-pass elliptic filter. And you go ahead and you plot the bunch of other graphs here that are going to pop up, the z-plane graph and the magnitude graph. And you can use these values to determine what your values for your cutoff frequency and your order of the filter should be. So after looking at that, analyzing that, and applying the filter, the high-pass elliptic filter, to the signal, you can see that we have eliminated the DC offset. The signal still looks pretty similar. It's just eliminated the DC offset, so there's not much noise filtering out in this stage. So once we have that, we now have that signal. The next part is to basically create a noiseless signal that creates or maintains the integrity of the original signal, but we want a very smooth sinusoidal signal. That way we can generate a clear peak in the signal, and this will in turn be created at the actual peak of the signal. So let me go ahead and run this, and I'll explain a little bit more. So again, we are generating magnitude plots, z-plane plots to choose the properties of this filter. So again, here we go. We get our filtered signal. This looks like it's not much different than the original signal, but when we go ahead and zoom in here, let's zoom into this portion of the signal. Perfect. So if you go ahead and look, this is the original signal from the high pass filter, or this is the original signal. There's actually two different lines right here. So if you're not the smooth sinusoidal line, but the one under it is the high pass filter signal. And then as you can see, we've generated a very smooth sinusoidal signal that mimics and basically hits its peak value around the peak value of the original signal. And this is what we're looking for. So this is perfect. And so choosing your filter or your low pass filter values for the cutoff frequency and everything like that will affect basically the peak of this sinusoidal signal. So getting this value right is pretty important. So next step is we have the high pass filter. The next step is to then put this through a peak detecting algorithm. So we want to grab basically the peak of this sinusoidal signal and plot that and put this and put that x value in an index where we can keep it stored to later replicate on the original plot. So we go ahead and do that down here in the filtered signal. So we're going to go ahead, plot this, and as you can see, we have a bunch of red dots now. So these are going to be our peaks that have been plotted on the sinusoidal low pass filter plot. So it's not quite on the original plot yet, but as you can see, it's pretty much in the correct area, maybe a couple samples ahead or behind of where it should be. But for the most part, it's actually at the correct value on the x-axis of where the actual peak is on the original ICP signal. So this is perfect. So now what we're going to do is basically take the index of these x values and store them. And then what we're going to do is we're going to replot them on the original ICP signal. But we're going to basically say at this x value, what is the y value of the ICP signal? We're going to plot the peak there. So we're basically doing an estimate, but it's a pretty close estimate of where the exact peak is. So we're going to go down here, and this is going to place the dot at the peak on the original signal. It's going to have almost everything from the original, from the whole code in this section. So as you can see here, it's all summed up. Actually, let's look at this first. So this is gonna be the final plot. So this is what, after you place the dots from this, you store those indexes of these x values, and you go back and you replot those x values. And then you plot the corresponding y values on the original ICP plot. You will be left with this plot, which is going to be our final plot. As you can see, this yields us our peak detection that we were looking for. It's pretty accurate if you look at it. For the most part, on this section at least, the peaks are pretty much spot on to where the actual peaks of the ICP signal are. But if you look here, we actually get a little bit of a discrepancy between the actual peak and the estimated peak. You can see a couple of these throughout, like you see right here. But for the most part, almost every single peak is exactly where the peak of the ICP signal actually is. So that's what this code does, is you can input this ICP signal, throw it through the algorithm, and it will pop you out the peaks of the ICP signal. And so I'll go back to the other part, where this part right here. And this was basically summing up everything we just did in one graph. So let's see here. If we zoom in, see if we can get a nice chunk. So perfect. So this line right here is going to be our original ICP signal, unfiltered, untouched, anything. I mean, I guess it has the peaks now, but that's the unfiltered ICP signal with the correct peaks. Down here is going to be your low or high pass filtered ICP signal with the DC offset removed. And then this is going to be your low pass filter as well, or the ICP signal put through a low pass filter in order to smooth it out, and allowing us to create a distinct peak where we can plot the x value where the peak of this sinusoidal wave is, and then we basically plot the y value corresponding to that x value, and then in turn we can plot the peaks of the original ICP signal. So that's my project for digital signal processing for Mateo Boy. I hope you enjoyed. Thank you.